All right, folks, welcome to the paper reading. This paper for this week today, Wednesday evening, January 24th, is LLM augmented LLMs. Now, this is an interesting tongue twister. Most of us are quite familiar and have been using retrieval augmented generations and so on and so forth. So we'll see what this is. And the subtext of that is expanding, or subtitle is expanding, what is the title? Capabilities through composition. I thought this was a very interesting paper because it, first of all, the results are good, but it also brings about a very innovative way to use, sorry, guys, innovative way to bring together different sorry, I apologize for that. Different LLMs to collaborate and come up with an answer. The intuition that I carry about this paper is, suppose I know a lot about, let's say, physics, and you happen to be an expert at chemistry, then one can easily imagine problems where to solve that problem, you and I need to collaborate. Right? And in a way, it opens up a new approach to collaboration between LLMs, or use the help of other LLMs, one LLM reaching out to another LLM, one or more LLMs, and saying, hey, could you help me with this because you are an expert in that area? That's a basic intuition. So I would say, suppose there's a problem that needs an understanding of some chemistry too. While I'm solving it, I would reach out to you and say, what about this? Can you help me? And that's the intuition. When you, like all great papers, when you read this paper, you wonder why did it take so long for this wonderful idea to show up? In hindsight, it looks so intuitive and just beautiful. So let's get into this. It's a paper from Google Research and DeepMind. So before I go into that, let me just remind you what are the other methods we are familiar with for LLMs, augmenting LLMs capability. 2 weeks ago, we did LoRa, a family of methods, if you recall. We also covered a few weeks before that, mixture of experts. There are other ways, for example, the merging models, like you take two models that are sort of aligned, and how do you merge their parameters, right? And that itself has become a little sort of a subdiscipline. There are open source projects now. For example, MergeKit is a very good project that helps you merge different LLMs and their capabilities. Then, of course, another way to do that is to use a mixture of experts, which sort of takes an ensemble approach, puts a gating function. We covered the mixture of experts, but now we do the mixture of experts. People are doing it with Mamba. Mamba is a topic that no one has requested me to cover, but if you guys are interested, I would love to cover Mamba in the upcoming weeks. So this is, think of it as a new entry in this repertoire of LLM augmentation. Let's read the abstract. The abstract says, foundational models with billions of parameters which have been trained on large corpora of data have demonstrated non-trivial skills in a variety of domains. We know that to be a fact. LLMs are very powerful. However, due to the monolithic structure, it is challenging and expensive to augment them or impart new skills. For example, fine-tuning is rather hard. If you want to fine-tune, minimum, we all tend to need at least a few servers packed with GPUs. Right? That's a fact of life. So it goes on to say, on the other hand, due to their adaptation abilities, several new instances of these models are being trained towards new domains and tasks. So that domain adaptation is sort of a fine-tuning. In this work, we study the problem of efficient and practical composition of existing foundational models with more specific models to enable newer capabilities. And this is the crucial sentence, I suppose. In this, so the words that are relevant are efficient and practical composition. How do we do that? To this end, we propose composition to augment large language models. This is the main thing, and this approach they call CALM, which introduces cross-attention between models to compose their representations and enable new capabilities. Salient features of CALM scales up LLMs on new tasks by reusing existing LLMs, along with a few additional parameters and data. Existing model weights are kept intact and hence preserve existing capabilities and applies to diverse domains and settings. So guys, I'll talk a little bit about it. See, when you try to scale or take a LLM, a large model, to new tasks, one naturally thinks all these approaches, fine-tuning approaches, LoRa, or fine-tuning the entire model, or things like that, right? Or do something with prompting. However, those things, as you will see, have limitations. In this approach, actually, you take different LLMs that are good at different things, just as I took the example that I could be good at physics and you could be good at chemistry. So we would be two different LLMs. And the idea is, how can you compose an effective, larger LLM without touching either your weights and biases or my weights and biases, but instead just putting a little bit of the glue in there that is trainable, just something there, right? That's what it is. So they illustrate this example using some models, which we won't go into. So in this paper, instead of going through it word by word, I will just bring out the flavor of it, give you a high-level explanation, and then we'll sort of review through the paper. So let me say that. See, folks, what are the ways of augmentations we know? For example, I'll just take RAG. Let's look at something about RAG. So guys, I'm throwing in ideas that to me sort of like, it sits somewhere in near there. In RAG, what we do is we say we have an LLM. Let's say we have this, this LLM. But this LLM can hallucinate, or it can come up with, or there are many things it may not know. So what do you do? You augment it with non-parametric or auxiliary information. You put a semantic search and retrieval from a corpus of documents, corpus of dots, right? Corpus of information. Nowadays, it can be documents, it could be videos, it could be images, whatever, like dots, videos, images, right? Audio, you have it. Database, relational database if you want, and so on and so forth. So you have auxiliary information sitting there, which may be fresh. The LLMs are prohibitively expensive to train. So you might have trained them in 2022. So lot must have happened since then, right? So you take auxiliary information, and given a user prompt, you first go and search for information that may be relevant, and then you sort of create a different prompt than the user. You take the user prompt, but you also augment that prompt with the search results from your retrieval. And then you take all your search results as well as the prompt and some instructions, and then you feed it to the LLM, and then you can make sure you can train it well. I mean, work the system well to check whether the LLM is respecting what you respecting the documents that you have. Obviously, there are excellent open source projects that sort of benchmark this behavior that you can use to make sure that your instruction at the top and the way you're using it does make the LLM maximize its use of the information that you get from retrieval. Right? So you get a retrieval augmented LLM. It's great. If you think about, for example, a semantic search, there too, you are, and this is a point that it sort of occurred to me. How do you do that? There also you use a sentence BERT, a sentence encoder. Well, not just BERT these days. Sentence encoder. What does it do? It takes a text and it generates a vector. Text I, it goes in, and a vector comes out, an embedding vector comes out. Vector comes out. So in some sense, this LLM is in a very simplified way using an auxiliary LLM, right? And a tool plus tool. For example, it may be using some form of affairs index, vector DB. Now, to get a whole set of results, XI, B, search results from the retrieval to better answer the user prompt. So that is a very quick summary of RAG. But observe one thing. In a way, the LLM is using another model to help it out, and a corpus of documents. So there is a resonance of that you will see, or a very, very vague resonance of that. The other thing I wanted to give as a background is, and if you recall, a few weeks ago, many weeks ago actually, many months ago, we covered a cross attention, and in fact we covered something called blip 2. Now, for those of you who are not familiar with blip 2, just ignore whatever I am saying. But very roughly, if you wanted to, for example, caption an image nicely, or ask a question about an image, and so on and so forth, one of the things you could do is you could take an image encoder, one model, which is very hard to train. Like, for example, a clip-like model, clips, whatever clip plus plus is these days, right? Take an image encoder, take an image, and then feed it in here, and you come up with an image vector encoding. And then what you did is you fed it into something called a Q-former, where the core idea is cross-attention. And we won't go into the architecture of that. And what comes out of here, you finally gave it to an LLM to describe. LLM effectively to decode and describe. And here comes your text result, right? And then in this Q-former, of course, you can also give it a text input. You could be asking something about the image. And the words that you use there is, cross-attention is the most important thing. What you do is you have some in here, a place at which the information coming from the image and the information coming from the text, they sort of meet to create a richer information in some sense and move forward. Now, the spirit of this paper is very similar in some sense to these two ideas. What it says is that, suppose I have, and by the way, in blip also, if you remember, I'll use this symbol, like a snowflake symbol is because a snowflake symbol that's become standard in the field to show models that don't change. So in blip, if you remember, you can take a big model, let's say big model, and another LLM, which are of course ginormous models. Those are frozen. But what you train is just a little, the only thing trainable is just the little trainable weights are here. And compared to large language models, which have hundreds of billions of parameters, or image encoders, which also can be ginormous, a Q-former, this in-between thing, which has a cross-attention, is a drop in the bucket, relatively speaking. It is just 200 or 180 million parameters or something like that, give or take 200 million parameters. 200 million parameters is 0.2 billion. Compare it to 200 billion parameter models that are the LLMs these days, right? So you just need that glue that sort of joins the information coming from image and the information coming from text, that glue code. And I find that in some sense, what the idea that is being talked about here is very similar. Suppose you have a model, which is now, let's imagine that here is a model that is a big model. Big model. In this paper, it uses the word model B. It is your anchor model, or the real. Think of it as the model that does the things, many of the things that you expect it to do. Then imagine that there is another model, model A, which can do something special. One example that could be given is, what if this is good at arithmetic? Another example in this paper is, what if it is what is called low resource language, some form of translation, right? So it has been trained on words like, let's take a language that most of us are not familiar with. For example, if you take a language like, well, I am part Nepali, so I will take a Nepali, a text in Nepali and a text in English. This little model, let's say, has just been trained into going from Nepali to English, or some very little amount of data. In fact, that data wouldn't be called training. These are called low resource languages. The word low resource means there isn't enough data, very little data. So when you give very little data to a LLM, what will that LLM do? Well, it will more or less go and memorize the data, isn't it? And you can see that all it will do is it will just do well on those things and do a little bit of generalization, but not too great a generalization. But suppose you want to give it a problem, the big model, which has not been sort of trained on Nepali, it's been trained mostly on English, then can you do things in Nepali now that you could only do with English, that only the big model could do? Wouldn't it be lovely if we can take a model that can do complicated things in language, in an English language, and somehow make it also do it in Nepali, right? That's the spirit. So the whole question is, suppose you get an input in Nepali or something like that. What does this language model can do? It can reach out to this fellow, model A, and it can say, hey, you're good with Nepali, help me out. And the model A would say, okay, let's do it together. You and I, let's work together and let's go solve this problem. Are we together? And that is practically the main idea of this. What you do is you put between these two. So these models are all frozen. MA exists. This MB exists. This big model exists. Right. So imagine something like a really big LLM. Think of it as, for example, you can think of it as a GPT-3 or some 3.5 or something like that. I don't know, or something. In this particular paper, they take Palm S reasonably, and in this little ones, they take Palm XXS, really a small model, right? So you're saying that a small model which can do just one sort of task well, let us now use it to augment a much bigger model that you would go normally. It is the anchor model, and help the anchor model do more. To do that, you keep the anchor model frozen. You keep the model, this auxiliary model, also frozen, this tiny model also frozen. So the whole thing is, then how will you train it to do anything at all? right? The way you train it to do is you, just like QFormer, the way it looks to me, you bring in another object and they just call it the trainable cross attention. You just bring in a trainable cross attention, and we'll go through the details a little bit, a couple of moments at a time. Yeah, a little, sorry, not a couple of moments at a time, small pieces at a time, till we understand how it works. So the idea is, this is small, and this is trainable. Guys, please. One, I'm giving a talk. Is it important? So this is, in some sense, like the QFormer. It will be much smaller, smallest of them all, right? So if this is big or very big, this is, well, let's say a normal. This is tiny, a tiny amount we are going to train through some so if you're training a very small model, you would agree that you need very small data to train it, isn't it? So that is the advantage. Now, let's look through other advantages of doing it. How we do it, we'll work through the math in a moment. The main the main advantage is you don't need fancy hardware. You realize that, right? It's such a tiny model, it will fit into fairly much smaller hardware. The training speed will be faster, right? Quickly you'll be able to train. There's only so much data, so many epochs you can go through that, right? You'll be able to do that. And one more thing, because both of these models, Model A and Model B, are frozen, there is absolutely no risk of catastrophic forgetting, isn't it? See, every time you take a foundational model and you then apply your own data to it, there is always the risk of catastrophic forgetting. Why? Because the distribution, if the distribution of the data, probability distribution of the data on which it was pre-trained is vastly different from the probability distribution from your specialized fine-tuning data, you run risk of catastrophic forgetting. So instead of improving, the model will just start getting worse and worse and worse. Right? So those are the risks that we have. Now, with this big idea, you realize that this paper is all about this thing. How does this magic happen? Right? How does this magic happen? That's what we're going to do. Go ahead.
Where do we start? So when we start the first LLM, so it will be only the small model A, right?
No, model A and model B exist. For example, Palm.
So in this case, yes, but where do we start initially?
Oh, you start with pre-trained models for specific tasks.
It will be model A and then you move into model B?
No. You just go download model A and model B. So suppose, for example, you want to do arithmetic, right? Go and get a model A which is specific to arithmetic. And model B is just any big large language model, like, right?
Then we are talking about the smaller versions of multiple model A's.
Yeah, you can even do multiple model A's. This paper doesn't cover it, but the way the architecture is laid out, that is literally the inevitable next step in this journey that will happen I expect it to happen pretty soon, right? Because it opens the door to that. Right? You want to do, so in this paper, for example, they take different kinds of model A's. One for arithmetic they do, right? One for coding, right? So you can train a model A to really have some sense of, let's say, Python programming. And now you marry it to a general purpose large language model, right? And then you will see the magic happen, and we'll walk through that magic in a moment. Subrata.
So I think it is very similar to MOD, wherein you can take different experts, right? Is it very similar to that, wherein you have a smaller model, larger model with frozen, and basically there are different MOEs who are working on it, and they're augmenting both of them. Is it very similar to that?
Yeah, let me answer that question. Subrata here asked this question in the audience. Does it not look like mixture of experts. See, in mixture of experts, what you do is you have these experts, right? And then you have a gating network. Now what happens is when input comes, gating network decides who to route the inputs to, right? To get, and these are your experts, expert 1, E2, E3, E4, E5, E6. Right? Now, there are two ways of doing MOE. One is to train the entire MOE, even the experts together, and you let them specialize, co-train the gating and the experts. The other way is that you get pre-trained experts, each expert in a separate area, and now you just train the gating function, right? And so in some sense, you can say, I can get really big and heavy experts, and all that the gating function has to do is just know if a user is talking about something, which expert to send it to. So there is a similarity of that, but gating function in itself doesn't directly use cross attention, right? So it doesn't use. So think of it as another approach to MOE. I would say that. See, it's amazing how many creative ideas you can come up with in this space, and that's which explains the huge number of research papers that are coming out. All right.
Also, can I ask you a question? This is Madhu. Yeah. One question that I have in this whole structure, since the charges, especially for enterprises, moving into this whole generative AI RAG structure, they're charged based on tokens passed, right? So in this case, are they going to have costly way of implementing their RAG structure? Because now you're bringing in the large language model in between for co-learning.
You're talking about the MOE, or you're talking about this paper?
This paper, actually.
Oh, this paper is basically saying, see, if you were to commercialize it, you would commercialize the entire thing. You would say, okay, here is a service I'm deploying, and what it is deployed for a particular task, and now I'll charge you per token. In other words, you have to go and train your this in-between layer, the trainable layer, and then expose the entire thing as a service. So it has, I mean, see, the input and output are still the same, right? Whether you give the input to only the anchor model, or you give the input to the SCARM, or this entire composition, the number of tokens remains the same for input.
Got it. So it's basically a one-time deal, not in a pipeline way, basically.
No.
Got it.
No,
Okay.
so you have to train this in-between box that is there. And so that's the magic that we will see how to make it possible. So first things first, suppose you bring cross attention. Just as a very quick idea, so let's go and look into cross attention. But before that, let's just forget about the cross and look at attention. Just a very quick, and certainly not meant to get you started with what attention is or self-attention is. If you look at self-attention, you realize that if you want to find out the self-attention for a particular query, how much attention it is paying to a particular token. Let's say that you have tokens T1 to Tn, right? Then you have to take every token, and suppose I'm looking at the attention vector, like how much attention this word, the cow jumped over the moon. So cow, imagine query is the cow's vector. Then cow needs to go and query every other thing, do a dot product with key of every other word, every other token, and come up with its attention vector, isn't it? So the attention vector AI would be this. Obviously, there is more to it. Actually, let me not. There is a softmax here softmax, and there is a D, right? So this thing, I'll just blow it out and this is not meant to be the softmax. Right? QI dot product with KJ. This is what, and by the way, it's not just dot product. The only reason I write it in this notation is because some people may introduce a transformation matrix in between also. Sometimes these days people do that. So that's why I'm not writing it as a way. And this is your VJ. So this was, remember, your self-attention. So you know that one thing is for sure. Each of these, QI, KJ, VJ, they all belong to some particular vector space, right? Let's say some vector space D, because ultimately the query is looking for its alignment with the key in that same vector space and the attention. So this is it. Now, if you remember this basic idea, now we can move forward. If each of the things have to be like that, our first task is to, in cross attention, if cross attention would mean that I will take QI from the anchor model. So it's the anchor model that is going to the anchor model B. It's going to your auxiliary model that can, for example, understand code or understand Nepali or something like that. And it will get some information from it. That information will come to it as key values and something. So we will be doing, what will happen is the cross attention will come here from the fact that the model B will give QB. Are we together? And now how will it give? We'll worry about it in a moment. And model A will give the other two, K and V. So these are coming from model A. By the way, I'm going to slightly depart from the notation in the paper. They use the model names as subscripts. I'll use it as a superscript just to be a little bit more clear or more aligned with the way I think. So now there is a problem. Where do these things come from? Let's think how we could produce this. So we have model B and model A. And let's pay attention to some particular attention layer or some layer, right? Some intermediate hidden layer in there, model A, model B. Oh, sorry, I'll always put model, auxiliary model on the left-hand side and the big model on the right-hand side in keeping with this paper. So imagine that you want to do cross-attention. The way you do it is you take some layer. So imagine that there is some layer. It's producing layer. Right? Actually, let me just layer will produce something. This is a layer. This is a layer that of I, and this is a layer in this. Maybe I can use a different language. Some other layer in the model, a jth layer. Right? What will this layer produce? This layer here will produce, let's say, it will produce a hidden state. Like as the input goes through, it will produce a hidden state, a hidden state. I mean, a vector will come out of this layer, right? Each layer produces a vector in a neural network, isn't it? Sort of is giving you it's emitting out certain, if you think of it electrically, voltages, and all of it put together is your vector, right? A certain activations. The activations all put together is your hidden state. Likewise, in this, it will produce a hidden state coming from the model B. So far, so good, right? Now, what do we need to do? We need to somehow get K, Q, and V, because if we are going to plant self-attention here, or sorry, cross-attention here, this guy must be fed basically vectors of the same dimensionality, right? So let's call that dimensionality D. It must be fed something of D. But the input vector Hi, this guy may belong to a completely different dimensionality. Let me just call it dA, dimensionality A. Likewise, this guy coming may belong to a vector space that is dB, right? And none of them might agree with, let's say, DC, something like this. Are we together? So the very first thing you would say, okay, that's easy. All I need to do is a linear transformation. This is linear algebra. I just need to stick in a matrix such that if I take if I take HI, and what can I do? I can apply this, right? A to this to produce, let me just call it the query part. No, not query, a key part, a key weight matrix. Remember how are KV and in a normal self-attention, if you recall, we produced KQV, KQV by doing what? You take the input multiplied by WK, you take the input multiplied by WQ, and you take the input and multiplied by WV. Remember, these were the attention matrices, right? These were linear transforms. You apply it to the input to get the KQV. So in the same way, no different, what we will do is we'll multiply it with the key weight matrix coming from A, and you will get a key coming from A from the ith layer of A. Are we together? So let me put just a reminder. I stands for the ith layer, and A stands for the smaller model A, small auxiliary model. So far, so good, guys. Likewise, what you can do is you can, again, from A, apply HI, and obviously it is coming from A, another matrix, a value matrix, to produce what? It will produce for you a VA from the ith layer, right? So in other words, what have you done? From HI A, you have taken linear projections. The word that you would use is, you have applied a F to it, a projection F. These are called linear projection function. It's a linear projection. If that word looks too messy, just forget about it. It just means that you multiplied with these matrices and you got what? You got Ki, the key vector, and the value vector from A. So far, so good, guys? This is easy. Now what? Likewise, you can leave and what typically you can do is you can make C the same dimensionality as DB. For now, let's keep it simple. Let's not have three different dimensionality. Guys, give me 30 seconds. I'll be back. All right, next. I'm back. So this is the linear projection part. In this paper, this is shown. Let me just show you where that little bit of magic happened. If you look at this picture, and I'll just blow this picture up a little bit, we covered this little part. This is your linear projection. Projection part in this big diagram. And we'll come back to this diagram once we have understood all of it. And then this is your cross attention. And we'll see what it does. So as you saw, from the layer I of A and to the layer J of, you took layer J of B, you are putting them together. So let's now again put them together and see what goes. So far so good. I hope you guys are with me here. Right? It is straightforward. Now what do we do? Well, it turns out that is the core idea. All you do now is you have this, and you already, of course, have a QB, right? A QB, J, is basically the hidden state, J. So now, do we have all the ingredients to create attention, cross attention? Of course. Now, what we need to do is put these together. We can say cross attention, or the standard attention equation. No, you just take, yes, you apply, sorry, thank you for pointing that out. I was going to miss it entirely. You're right, Q. You do that, and you also transform this, right? So now you have transformed the query, you have transformed, actually, for that reason, there is no reason. This is, I shouldn't convert it to the same dimensionality. B can be very different. This matrix will take care of it. So there we go. Now, all we need to do is apply the attention to K coming from ith layer of A, Q from the jth layer of B, and value coming from the ith layer of A. Right? How do we do it? No different. Like you apply the softmax first to what? To the dot product between Qj from B with key of A and I again, and then you do the usual stuff, whatever it is that you do, and then multiply it with V coming from I. And this is your cross attention. There you go. You have your cross attention, right? It's just attention. It's just that information is coming from different places. Now let's think about the implication of this. What is it doing? We are going to end up with an end result, a new mixed cross attention vector. Let me just call it X A something like this, because it has benefited from both of them, isn't it? Cross attention is where they learn to glue together. And if the cross attention is the end and the projection are the only two functions that you will train in the model, you realize that all you're doing is teaching each model to understand the other model. Are we together? And to collaborate, to figure out how to collaborate in solving problems. That's all you're doing. And if you do that, then the rest of it is, of course, you guys all know, it is the multi-head aspect is not to be forgotten. So what you do is, now what you do, this vector that comes out here, the hidden state, actually, let me use the word that they use, a hidden state. Yeah. So what you do is, this thing at JB, which just came out, now you add it back. The cross attention, let's say it produced H, let me just call it A plus B, A and B composed from this attention mechanism and so forth, right? And what you do after that is, and this was your big model B, it came here, information H, J came here, it went in here, the model A came here, and the layer I produced HI, which went through some transformation, the linear transformation, and then it finally went in here. What came out is this. Now what you do is you treat this as a residual. You use the residual trick. What is the residual trick? You don't let Hj propagate forward. You instead take this and you add the two up. You bring it back and you add the two up, right? So that to the next layer of the main model, your anchor model, not Hj would normally only Hj would have gone up, isn't it? A hidden state would have gone to the next layer above it. Am I making sense, guys? Think about it this way. Information is propagating, transformations, activations are happening, right? And output of one layer, lower layer, goes to the input of the next. But then here what we are doing is we are taking the output of this layer, and as a residual, the technique is that of residual. So you're bringing in this output that we got from cross attention. You're adding it up, right? And that is what you're going to the next layer. Does that make sense, guys? Right. And again, in any model these days, you don't have just one attention head. You have multi-heads. How do you do multi-heads? That part is fairly trivial. You just concatenate each of the output of each of the heads. Suppose you have k heads, you will just do what? You'll concatenate all of them, and while you're at it, you'll apply one more transformation output, and that becomes your and then of course in reality you'll do that. You'll do some layer normalization, you'll do some while you're at it, feed it through a few feed forward layers, right? I call feed forward layers it's like peanut butter and jelly. You always put it between your slices of bread, right? So you do that, and that's your multi-head. Well, that's what you did between two layers, but that doesn't prevent you to do it again after a few layers and again after a few layers. And this is what you do. Think of it as two buildings of different height, and you're just picking some floors here and some floors here and building little bridges between the two, this cross-attention bridges between the two. Are we together? Right? And so what happens is, why would you do that? See, remember, the general belief is that lower layers are still dealing with lower sort of abstractions. As you go up, they're forming higher order representations. That's one way of thinking of it. So you want them to be collaborating at multiple levels of understanding the input, right? So to do that is the gist of it. Now let's walk through this paper a little bit more carefully and see if what I said makes sense, right? We will first of all start with this image. So this image says that, see, take a small model, auxiliary model like MA, and take the model MB, same notation. Is it making sense, guys? Hopefully this picture now makes sense. This is the main cross attention, and this is linear projection just for alignment, to come to the same space, vector space. This is it. When you do this, actually, what you expect, and obviously they are showing a little bit of the results here, what happens with this model? You can ask it questions that would be hard for model B to do without taking the assistance of model A. Right? So for example, if you say translate from blah, blah, blah to English, it turns out that even simple things, like for example, from Nepali to English, you need a Sherpa there to help you out. And your model A is a bit of a Sherpa that will help you in the translation, help the main model into the translation. You'll see that this works in the experimental aspects, but at this moment, let's stay at the level of the concepts. Likewise, you could give it a small model A that has been trained on GitHub code and only on GitHub code, on nothing else. And then you can, so it's only very good with code, open source code. Now you take a general purpose large language model, B, and if you were to ask it, what does this code snippet do? It might scratch its head and not give as good an answer. But because it is getting the help from model A, which specifically is good at only one thing, code, then model B is able to answer that much better. For example, in this particular case, it is saying, hey, the model B, this code, the Python code snippet is actually implementing the classic word game of hangman, right? Or this one is saying, let's say from Nepali, you ask it to translate. It does a much better translation, and it says, hey, what is being said is everything but the kitchen sink. Right? Are we getting a flavor of it? And one of the interesting things that it says is that the amount of data needed to train CALM, this is composition, augmented language models, right? This particular architecture is very little, notably CALM generalizes. So this part, I think, is worthy of note. Generalizes to the entire key value set despite training with arithmetic examples spanning only 20% of the keys. Means it not only, whatever data that you use to train model A, the smaller model, it takes even smaller amount of data to just get it all aligned and fixed. Right? We'll see that in a moment. So now it sort of talks about other ways of creating augmented models, LLM augmentation. So parameter efficient fine tuning, big topic. We have covered it in fairly good details. Just 2 weeks ago, we did LoRa, a family of fine tuning methods. Now, how would you compare CALM to LoRa? This approach to LoRa. See, in LoRa, what do? You do low rank adaptations. You put auxiliary models that you train, entire model that you train. That model is not paying attention to the main model. Main model is frozen, isn't it? So you just, you let a trainable auxiliary model get fully trained. Problem is, you can train it only if the problem you're solving is not different, too far away from the problem that the main model has been trained to solve. You can't apply it to an entirely different domain, right? It doesn't work so well. That's the thing. Model merging, of course, MergeKit open source is there, and there are many ways of doing model merging by doing arithmetic merging and very fancy merging and so on and so forth. It has been there. But here the main problem is these two models have to be relatively aligned, right? You can't do it with a tiny model and a big model in the way that you have here. And model and task composability you could use. And so there are different approaches you can try. I won't go through all of them. Model as tools, which is the agent way of thinking, that the main model will treat this other models as its tools, right? It just needs to figure out that I need to reach out to that tool. And so it will break it up into subtasks and try to do it, right? Again, it's not as cohesive, right? Now we come to this. So this goal is a composition. You compose it out of 4 elements. Model A, we understand. Let me increase the font a little bit more. Model A, we understand, is the auxiliary model, right? For example, a model that understands code or a model that understands Nepali. This little, on the little bit of data that it has got, which probably means it has been memorized the data. Model B is your main anchor model. This is the parameters of the, what is theta c? This parameters represents the parameters of what? The linear projection as well as the cross attention. Those are your only parameters there, right? Of those parameters. And data, this is a little bit of data that you need to fine tune this guy C, the in-between guy, the cross attention there, right? Or the little box in the middle. So that's what it is. So let's do that. Let's see how it goes about it. So it says that let's take a layer LA and from LA and LB, set of layers. How do you pick layers? What they have done is they have said, okay, we are going to do at a certain number of levels, 5, let's say 4, 5 levels here, 5 levels there, we'll do it. right? Now, what you do is you don't do consecutive layers because it's too thin. Like the thinking at this level and the thinking of that level, they'll be not vastly different. The idea is you have to skip a few levels to get an entirely different kind of representation. I'm guessing that that must have been the intuition, that skip a few levels, have a different form of representation emerge in both of these models, higher level representation emerge, and then we'll again merge, we'll again compose there, and then we'll go a few layers and then again compose. So you do skip. Now, I think somewhere they mentioned that they typically go to the every fourth. In this experiment, they took every fourth layer, right, and went about doing it. So now what are the things that you learn? Projection is to be learned. So this is easy, guys. You create projections, right? You project it. Why are we, for each of these different towers, we are doing projections there, but we'll leave that there. Now, let us deconstruct this from the bottom up. This equation is very simple. This is this. Does it make sense, guys? First, we need to create the hidden state of A from the ith layer. This is exactly what we talked about, if you remember. This equation is the same as, let's try to align it here. What they call this. Are we doing up here? Sorry. This part. This is the part here, I should have said. This part is here. This is the projection part, right? So you get the key and the value through projection, right? I hope it is, guys, give me some feedback if it is not obvious. I hope I've made it fairly obvious, right? So what will you get here? You'll get the key and the value coming from the A model, the small model, and the query vector will come from the B model, the main anchor, big model. And after that, it is just cross attention. It is just attention. And then attention, because there are multiple heads, what do? You concatenate all the attention heads and multiply it with, while you're at it, with one more output matrix. This is again going back to the classic attention is all you need paper of 2017, no different, right? So this is that. And so they say that they use the word that finally the cross attention output is added as a residual connection to the layer. Mathematically, it's obvious what they're doing, right? You take the initial signal and then the output of that, what that in between box is saying, you add it, right? That is your residual connection. And therefore, you now have some things that's informed, or it's a joint agreement between these two models, isn't it? That's that. Then you take some data and you train it on the data. This part is easy. If you don't mind, I will sort of skip through this. And now let's look at the experimentation. First of all, they took arithmetic, and what they did is this is worth looking at, because the other three, they talk about 3 experiments. All 3 of them are pretty remarkable. So what they did is they generated a repository of key value pairs, right? So key value pairs means A, B, lots of them. A1, B1, A2, B2. Now the question is, what are keys and values? So we'll come to it. They create 3 data sets, right? One of them, what they did, first thing they did is they said, okay, you have a dictionary of words, right? NLP, the first thing you start with is a dictionary of every token maps to every token, or every word has a index, a number associated with it. I'm the 14th number, I'm the 26th number, so on and so forth. So what they did is they put the key here. They say that this constitutes the knowledge artifact. The data set maps expressions in DKV expression to where the keys are replaced by their corresponding values. So for example, if you say, take a token, for example, like 1, plus 2, right? Or 1 plus 2 plus 2 or something like that. What you do is you just replace it with the token value. Here it is K1, K2, and here they're taking, oh, by the way, they took the example of 10, 22, minus 24. So you create a pair like this. Now you notice that to you, it may seem that this is A in our notation, and this is your B. This is the value of the key, or key and value, right? As far as you're concerned, it still just looks like tokens, right? You replace it with this. You create this key value substitution data set. The idea is that can you train a machine given this key to produce this expression, right? Now, if you ask large language models, the typical large language models, it won't be able to do something like this. You'll find it pretty hard. Then you try to create another data set, it's totally in your hand, in which you take the same key, but you replace it with the actual arithmetic evaluation. You know that 10 plus 22 minus 24 is 8, right? So you put 8 there. And then the third thing that you do is, this is a numeric arithmetic, purely numeric arithmetic data set. You say 10 plus 22 minus 24, and then you give the answer as 8. 3 data sets. Why would you do that? Right? We'll see why they did that. What you do is, you can test model A and model B, how well they do in each of these. Right? Given the key to produce the value. Key as input, produce value as the output. Let's see if it is able to do it. And the results are quite interesting. So remember, a KV substitution is the hardest. Right? You're given a key, which is 3 tokens, right, with a plus and so forth. And then you're giving it an output, which also is 3 tokens, is numerical representation of the tokens. Model B, which is your anchor model, does disastrously on this. Do you notice that? It's pretty disaster. It's pretty much a disaster, right? Then because it's not trained with like, again, it's not trained KV math. KV math is NumPy, num math, right? Is there, and KV math, or KV math, this thing for 3 tokens to produce a number, again, it has not been trained on. So once again, it does badly here, right? The only thing it seems to do reasonably well is the KV arithmetic, because it has gotten trained with elementary, you know, that if you go to ChatGPT or any of these, you give it an elementary arithmetic problem with words, it seems to get it right, right? So it seems to get that right with 73% accuracy, right? Now, let's look at model A. Model A is pretty good with doing just this representation from tokens, string tokens to this numerical tokens. It does a pretty good job of it, but it does miserably on the other 2 tasks. Right? It doesn't do a word to, yeah, go ahead.
I have a really simple question. What is the K1, K2, K3? What does that signify? That I'm a hard time understanding that.
Oh, just 3 tokens. So for example, it could be, no. You take the token representation of 10.
Oh, the index,
That's right.
Oh,
that is right. That's what you do. Yeah. You try to do that. And then you realize that obviously models have not been trained on that. The only thing that has been trained on that is A, because you just trained it. And what will it do? What would model A do if you try to train it on that data? It's a tiny model. It will just go and memorize it, isn't it? And you can see how well it has memorized, 98.1, right? It says, yay, I got this right. But then on everything else after that, it's a disaster. It won't do well, right? So if you look at the values, let's see what are bad values. You agree, this is bad value, this is bad value, this is bad value, this is bad value, right? So what you notice is that the real task that you wanted to do is a thing like this. This is what you really wanted to do. A math problem given in words right? And a number, the correct answer coming out of it. Does it make sense, guys? Oh goodness, these days in schools, it's a bit of a nightmare. All the math books now in California, instead of giving math problems as math, it's given as word problems. And God forbid if you don't understand English too well, right? So anyway, something like that. So they need to bring in this model there, all the students. So now you notice that remarkably, look at this. A model that has been, see how well it does. Right? A model that was not capable, look at, I suppose I should highlight this fact. No, this fact. Oh goodness, why am I not able to change color? Let me do this. Sorry guys, I am having a bit of a technical difficulty here. Okay, I'll just write it down, this part. MB, the anchor model, went from being 0, completely incapable, to becoming really good at it. Word problem to getting the right answer. Guys, do we see that? I don't know if you find it impressive. I think this is pretty impressive that it could do it at all, right? And far more impressive that it did so well at this. Oops, sorry guys. Give me a moment. This is not behaving. So I'll start this one note again. All right, with some luck. Let's see. Yeah, guys, do you notice how much of it? A base model, MB, which initially couldn't solve this problem, now all of a sudden can solve this problem very well, isn't it? And even model A, the initial model, MA also couldn't solve that problem. Do you notice that that also is doing very badly? But now in this word math problem, while individually they are weak, the whole is much more than the sum of parts, and impressively more. That's the main result of this paper. And I'll gloss over the other ones. The second one is for languages. And you can see, I won't go into that, but you will see that it does very well for languages too. For low resource languages, it begins to do very well, if you noticed. Right? Compared to the base model. So for low resource languages, compare these two lines, CALM versus MB, right? And you realize that not always, there's scope for more improvement, but consistently you begin to see improvements, right? Because for low resource language, frankly, there is a data problem. What about for high resource language? In this whole process, is it, for example, going through catastrophic forgetting or any of the bad things? That is shown from this result that it is not. In fact, for languages that the base model was trained on, like English, it still continues to do very well, isn't it? Not only do well, it actually improves even there, right? So here, obviously, the MB is a model, MA is a model for other language. MB is your anchor LLM, the main LLM, right? Whose capability you're trying to augment. Right? Likewise, you can go and see for code, it is even further impressive. So you can give it a piece of code these days to language models and say, okay, what is it? And it can answer some question. But if you pair it with a smaller model that has only learned coding, GitHub code, right? Then what happens is the results are, again, well, better. Sometimes, actually, if you look at some of the core languages, for Python, I suppose Python is something that people often take. You can see what a level of improvement there is there, right? So that is it. That is the gist of this paper. I won't go more into it. And there are different ways to look at it. You can see that this on various coding tasks and so on and so forth. See, you can do code to text, text to code, ask a question about code. You can code understanding, code to text. You can do all sorts of things. The last one is, I believe, code to text. Text, explain what this code is doing, right? So it will do that. And here are the explanations. There's code completion. You write some lines of code and you ask it to be your co-pilot and complete it. You can do a text to code. Can you write me the code for this? Which seems to be the most common request from developers these days. Then you have code to text. You just inherited some code and you can't make head and tail out of it. You ask it to explain it to you, right? And so it seems to be a good approach. I'll stop there. I think we have been talking for more than an hour. Anybody wants to ask a question on record? Is it clear, by the way, guys? Was it simple to understand? I'll just recap by saying the magic is to not do very, like, for example, if you have two models, a big model and some auxiliary helper models, you can put it together in many ways. Like one is you can say, okay, I mean, for example, you can not have an auxiliary model at all. You can just fine tune a LoRa, but LoRa you can't fine tune unless you're pretty close to the same domain. You could use a mixture of experts approach, but then you realize that mixture of experts approach would have tough time because one will be good at math and the other would be good at language. But you need something which needs both, right? And the moment you need both the abilities, that's where a cross-attention based, something that collaborates, forces a very close collaboration between the two models, kicks in. And this is a fairly straightforward way to enforce close collaboration. We might as well call it the close collaboration architecture for LLMs. All right, folks. So anybody who would like to ask a question on record, go ahead. Okay. You go ahead.
What I wanted to ask, if we were to implement this on our own, what is there to train? Is it just the W matrix?
It's just the in-between little guy. That's it. Yeah. And that is the main value that this algorithm brings. What you have to train is just this bit, the linear transformation and the cross-attention layers. Right? Of course, there's a little more to it, guys. It isn't just the attention. Within the attention, there's also layer normalization. There is some, a few feed-forward layers, and they will have their weights. But basically, see, that's the glue. That's always there. You can keep it. But basically, the linear transformations and this cross-attention. That's all you have to train. Actually, when you think how terribly expensive it is to train an LLM, the Anchor LLM, the very fact that you can do it is amazing, right? You can leave the Anchor LLM alone. You can leave even your specialists alone. There's little auxiliary models alone. You're just freezing them. And you're saying, we are going to take, oh yes, one part that I must mention. Thank you for asking that question. How much compute cost do I really need for doing it? It turns out that's the last sentence in this paper.
My question was about that.
Okay, so look at that. If you look at, so MB, by the way, here when they use the word training, they mean fine tuning. So suppose you had to give your LLM, the big LLM, Anchor LLM, MB, a new ability. What will you do? You will get that data to fine tune the big model, isn't it? Mm-hmm. So relative to it, how much effort did you have to put? 2% of the effort, 2% of the cost. Isn't that nice? Right. And suppose you had to train even the little auxiliary guy first on the data, but then also it is still a pretty small, right? It is less than, it is basically 1 or 2 orders of magnitude smaller, right? So definitely the way forward, isn't it? So guys, a 2 orders of magnitude smaller is the difference between a $40,000 H100 and a $400 video card, GPU. right? I don't know if any of them, maybe 2080 or maybe 3080 or something like that can be got for $400 or something like that. Imagine getting a $40,000 versus $400, right? It's a huge difference. One is something that only rich corporations can afford. One is something that you can put in your little workstation at home.
So that's the main objective of this split up, and then we could have put the supermodel itself, right? Like instead of model A, they could do the same training instead of the supermodel itself.
How would you do that? This is essentially a supermodel architecture.
So right now, like for example, if the language or any of the things, you can put it in the model B itself, right?
Yeah. So that is called fine tuning. That is called fine tuning. And what it is pointing out is, see, the main problem with fine tuning is, and this is it, one H100 or A100 won't do. You need a server. Typical servers will have 8 of those or 16 of those based on which one you buy. And then you need many of those servers to fine tune. It's very, very expensive. And one of the big thrusts of 2023 has been that we really need to find a way to train or fine tune or do domain adaptations or augmentations of LLM without being Google or OpenAI or something like that. Right? Well, interestingly, this paper has come from Google. It's a wonderful thing. But see,
scalability and cost both
is much better. Yeah, you can do that. See, with this low cost, it means that you can create a lot of augmentations. And the other good thing with this architecture is you don't have to augment it with one ability. You can keep on augmenting the base LLM with multiple abilities, right? And that they say is the future work in this paper at some point.
Asif, we have 2 questions in the chat. I'll try to cover them. The first one is, how does the routing work with this one? I think you may have covered this already. I don't have the context exactly when this question came up, but the next question is, what data set is the cross attention part trained on?
Oh, you just take a subset of the data set you train model A on. Quite often. Or you see, ideally, you should create a data set which is specific to the task that both have to do. You can't do alone. Like in this case, they trained it on a task like this. See, if you think about it, this task, which was somehow derived from the data set, a KV math, you need to create a task, a small data set, which is truly represents a joint task or joint collaboration between model A and B. Right? You don't have to create too much data. The data set sizes are pretty small. You're good. The routing part, I hope I explained. This is the routing part. Let me decrease this. This is it. Model A produces a hidden state at any given, and there'll be, of course, many such collaborations, but it produces a hidden state which goes through a linear projection, then feeds into cross attention, and it produces the K and the K and the V, and the model B produces the Q. Right. So this is the routing of information coming here. Now the output of the cross attention. So these are the inputs. The output of it goes back to model B and as a residual to be added to the output of model B. So in other words, model B's real output, let me put a tilde, is the initial output of model B plus the HA, the cross attention part that came through. That's that. I hope that answers the routing problem, the routing of information. You have a question? No. Okay, go ahead.
You said there are many levels that we can do this on.
Oh yeah, you keep on doing it all the time.
So does model A and model B, do they need like a similar amount of levels? For
No. All you need to do is, suppose they say that one has 10 levels, the other has 100 levels. Well, pick 3 levels here, and now you have to pick only 3 levels here. You don't want to, typically you don't want to like pick more levels here because then you'll have a cross.
Right.
In this paper, they kept it very simple. Guys, the person who asked the routing question, let me know if it is not clear, I can answer it again.
Yeah, it was me, and it is more clear now. The only thing now that come to my mind is like if I have multiple smaller auxiliary models,
Yes.
how would be the routing at that scenario?
Yeah, that is something. What at this moment, the way it looks though, that see, you have, so think about it like this. I have, imagine that here's the composability of it. Here is the model B. This is your mother model, right? The anchor.
Mm-hmm.
Now imagine that you have a library of two things. Let me call this guy in between. What should we call this guy? Let me call it potato. I mean, I don't know, it's silly. Potato, right? So you have a library of potatoes. And each potato corresponds to one model, auxiliary model. So let's say that this is a potato 1, and this is model A1. This is potato 2. So there must be a model A2, and so forth. Actually, I put superscripts at the top. So let's put the superscripts here to be consistent. Model 2. And so what you do is, suppose you need some capability. Today you feel like doing arithmetic, word arithmetic. What will you do? You will do model B, wire it up with potato 1, which is for arithmetic. And then you'll load the model A, arithmetic model A, right? And you realize that right away you got it. You immediately you take model B, you put it together. Right away you can do arithmetic. Then a little while later, suppose you want to say, hey, remember these are frozen models, so you can keep on composing on demand, right?
Mm-hmm.
You want to get the potato for let's say cold, right? Plus, and get the model for the auxiliary model for code, right? Likewise, you want to get a model for, let's say, lesser low resource language like Nepali plus model Nepali, an auxiliary model for Nepali. There you go, right? So what it means is that once you have the mother model, a good thing, and you just need to create a library of these potatoes and a library of these auxiliary models.
That's very helpful.
And you can just drag it in on the fly as needed.
Yeah. Is it possible to does the paper mention that is it possible to use multiple anchor models? Auxiliary model, not the anchor.
Yeah, multiple auxiliary models. Yes, it is possible, and in fact, that's what they have given. They have mentioned that is the future work to be done. So let's wait for them to come out with the next paper in which they show how well, when you put auxiliary models together, it will work. See, the architecture allows you, right? Because these are cross attention. We have all this merge kit and whatnot. We should be able to merge lots of potatoes and lots of auxiliary models, each potato reaching out to its own auxiliary model. We should be able to do that, right? Now, how well it will work experimentally, these guys seem hopeful, but let's see.
Yep. Thank you very much.
Any other questions, guys, on the record? Oh, you one more question. Okay, go ahead. Please go ahead on the audio and the remote.
We don't have anything in the chat, so we're good to go.
You're good to go. Okay, I have a question here in the audience. Go ahead.
I was thinking of just being creative about this. For example, if you have a document English and Nepali together, are we able to make a mixture of experts where we have a regular model?
Yeah.
And then combine that with this augmented LLM.
Mm-hmm.
And then use my trainer where it knows how to route inputs.
Excellent. Why not? That's certainly definitely a possibility. So somebody said, well, how about this? We take these combinations and treat each combination as an expert. One is an expert now a better expert at this, and you can now try some form of mixture of experts with even high level of composition and things like that. Why not? You can try. I suppose you can try many different things. This opens the door. Good thing with these papers is they open a door to a new possibility. And now let's see how creative people can be with all these things. So, folks, I am going to do two things. I'm going to stop the. I'll stop the recording.